Hi everyone, my name is Maya. I'm a grad student at Scripps with Helen Fricker, and I'm really happy to be convening this session. And we're going to start off with a talk with probably one of the better titles of this meeting, so by Ben Smith, talking about how ISAT2 is bathing the world in soothing green light.
So I'd like to thank Tom Newman for putting together most of these slides and coming up with this fantastic title, and what I'm told is an especially good abstract as well. Tom finds green light really soothing. The light from ISAT2 is about the same color as this laser pointer, which I don't find soothing at all. If I started playing that around the room, you guys would not be soothed either. But it's
But
happening.
if I were a cat.
If you were a cat, you'd be all over this, but you would not be soothed at all. So the mission overview so far is that it's going great. We launched a little bit more than a year ago from Vandenberg Air Force Base. That's the rocket going up. It was spectacular. We turned on the satellite about 2 weeks after that, started emitting light in October, and then we first collected science on the 14th of October of 2018, which was a great day. Since then, we're well on our way to meeting our science requirements. We're getting great data. We're measuring ice sheet elevation, sea ice freeboard, and vegetation canopy height. At some point, we had emitted 317 billion laser pulses. We're probably well advanced from that now. And the initial data look great. We're seeing accuracies better than 10 centimeters vertical and less than 10 meters horizontal. So even over fairly steep slopes, we're making accurate measurements. The release 2 of the data are out now. They're a minor advance over release 1. You should be able to get them from NSIBC through June 25th of 2019. So about 2/3 of a year are available, and the next batch of data will come out soon, which will take us to having a year of data available. ISAT2 was specifically designed to make ice measurements. It was specifically designed to measure repeat tracks over the ice sheets. So we've got a really dense set of data tracks that go to 88 degrees north and south. So we have 1,387 tracks per 91 days cycle, and we're designed to repeat those tracks exactly. This is a subset of tracks. This must be a few days worth of tracks here. But when the tracks are laid down in their repeat configuration, we have a track roughly every 3 kilometers in Antarctica. Somewhat worse than that in Greenland, but due to some accidents early on in the mission, we actually have a really great set of non-repeat tracks that have measured the ice sheets once at really high density. You can get a picture of these ground tracks from the ISAT2 science team webpage, and there are lots of other good things there, like videos and our famous the photon video showing how ISAT2 does not work. Our measurement concept was to make these repeat tracks, so on the set of 91-day repeat tracks. But we realized that there were fairly large gaps between the tracks, especially in southern Greenland. So we persuaded the engineers to build us an instrument that measures 6 tracks on the ground, and they're organized into 3 pairs. So the pairs are spread out by 3 kilometers relative to the nadir track beneath the satellite. And on each of these tracks, we have a strong beam and a weak beam, which are spread 90 meters apart. And the 90 meters were designed to encompass our pointing uncertainty, so we were sure that we'd be able to hit 90 meters again if we flew the same tracks again. And that gives us the surface slope, and we can monitor the surface slope as it changes underneath the satellite. And because the tracks will overlap one another, we'll get precise repeat measurements. We have one high energy beam and one low energy beam. The high energy beam can get through fairly dense clouds. The low energy beam, when it's clear, will give us this surface slope measurement. And we figured it was better to see through a lot of clouds almost all the time than to get equal measurements between the 2 beams. Early on in the mission, we had some teething troubles where we were telling the satellite to point to its repeat tracks, and it wasn't measuring those repeat tracks. And worse yet, it wasn't telling us where it was making the measurements. We figured out what was going on sometime in March, after a few stressful months of not understanding what was happening, and we post-processed those early data. So the post-processing picture shows us that we were a couple of kilometers off the repeat tracks. We tried to correct for that and got closer to the repeat tracks sometime early in 2019, And then in March, the button popped and we understood what was going on. And we told the satellite to point to the right track, and it started pointing somewhere different. And then we told it to really point to the right track. And since the end of March, we've been pointing where we wanted to be pointing, give or take something like 6 meters. So our pointing accuracy is drastically better than it was designed to be once we learned how to drive the satellite. So this is the plot of our cross-track offset prior to March 1st. Then in March, we started pointing somewhere, but not exactly where we wanted to be pointing. And if I plotted this now, all of these tracks would be green, which would indicate that they were pointed exactly where they were supposed to be pointed. This is a first look at the geolocated photons. So ISAT-2 measures the heights of individual photons coming back from the ice sheet surface. If you jam a lot of them together, it's crystal clear where the ground is. There are also this collection of photons that came from the sun, and those appear with equal probability above and below the ground. So ATLO3 tells you how high a photon is. You can see the surface clearly here. And then we do some processing to figure out which ones actually came from the surface. So this is all the photons, including the solar background. This is a plot just of the photons that we think came from the surface. So you look at this and you can tell by eye where the ground is. And we classify these as, we're sure this is the ground, this might be the ground, this is close to the ground, and noise. We can do this even in pretty adverse conditions. This is Disco Island in Greenland, which is a collection of giant mountains with a small area of glacier on it. And some of these slopes are well in excess of 45 degrees, and the tracking algorithm finds the ground just fine. This is pretty hard to do, pretty simple to do with ISAT-2. It would be extremely hard to do accurately with a radar altimeter. And ISAT-1 would have some trouble here too. Looking at the quality of our latest release, these are measurements where we managed to get the scanning laser altimeter ATM in the field at almost exactly the time that ISAT-2 was flying over the top. So these are measurements over sea ice. It's pretty rugged. You probably can't read the scale, but this is a couple of meters here. We've got ISAT-2 laid over the ATM measurements. I think there was a small vertical shift to bring them together. But we've got an R squared of 0.98 and differences of a small number of centimeters between ISAT-2 and ATM over pretty rough topography. Over smooth topography, we're making calibration measurements now, planning to do this 3 times over the course of the instrument. We send some lucky people out to 88 degrees south to drive along the place where all of our orbits converge, and they drive 15 or 20 degrees of longitude along that pole hole, and we can make direct comparisons between the ISAT-2 measurements and the GPS measurements on the ground. We see biases of 1 or 2 centimeters, depending on which beam you look at. We're seeing standard deviations of less than 10 centimeters for a small number of photons for each comparison. So these are very, very high precisions and high accuracies. But these are still photons. The first product that tells you about surface heights is ATLO6, and this is an early example that Nick Holschuh put together, just demonstrating the correspondence between photons and ATLO6. ATLO6 takes collections of photons from 40-meter segments and tells you what the slope and elevation of that segment is. So under clear conditions, it's getting between 150 and 600 photons into one of these segments, depending on whether you're looking at a strong beam or a weak beam. And this is in somewhere in the Berg Glacier area. It's a pretty rough area that has some crevasses. You can see that there are returns from the bottoms of the crevasses. ATLO6 gets a little confused in the crevasses, but does something fairly sensible with the surface elevation there. In smooth areas where there's no crevasses, it just tracks the surface as well as you could want it to be tracked. We also give you a quality metric for this. It's called ATLO6 Quality Summary. When it's 0, the data are good. And this lets you get rid of all of the weird looking segments that you first see when you first open one of these files. Looking at the statistics of this compared to the ATM survey at the pole hole, we're getting per orbit errors on the order of 2 or 3 centimeters, again, depending on what beam you look at. And then we can look at crossover differences and plot the crossover difference standard deviation against slope. And that gives us an estimate of our pointing accuracies. This is a plot that Johan Nielsen at JPL put together. And again, depending on which beam you look at, we're getting between 6 and 10 meters horizontal precision for ISAT-2 and crossover different statistics that are like 5 or 6 centimeters. So again, fairly high accuracy. So ATL06, again, is the land ice height. This is the first place where you can just start to feel like the satellite disappears and you just have measurements. And so we can watch ATL06 put together measurements over Antarctica month by month as the mission went along and end up with, I think, all of the measurements that we had as of April, which really blanket the continent in a very dense set of measurements. This is including those off-pointed measurements that we got early on in the mission, which have now been geolocated accurately. They're just as good as any other measurements, they just give you better coverage. For Greenland, if you make your dots slightly bigger, we're getting almost as good coverage. So the first thing that one would do with these things is to make a difference map with ISAT-1, which has been done and submitted. So this is a preliminary figure from that study, and it shows you all the things that you would like to see. So there's some really beautiful patterns of change in the Cycle Coast. We're getting the large drawdowns in Pine Island and along the coast, the Amundsen and Bellingshausen coasts, and some stuff in the East Antarctica. The thing that was a little bit surprising was the magnitude of some of the elevation gains, or the persistence of some of the elevation gains in the Drowning Maudline area. And so this is a manuscript that's on its way to great places, hopefully, for both Antarctica and Greenland. We've also started making our first measurements of elevation change within ISAT-2. So these are ISAT-2 versus ISAT-2 measurements, basically crossover measurements. There's a stray track. We usually try and eliminate anything that looks like a bad track from the data before it goes to NSIDC, but that one appears to have squeaked through, at least in the preliminary data. But we're seeing the thickening in the ice stream C area. We're seeing the thinning along the Amundsen coast. And all of the area around the edge, you can't see it at this scale, but if you zoom in, it's pretty clear that we're watching it snow. So you can see that depending on when a particular track was laid down, you get a different DHDT measurement from that. And that's just how much it snowed early in the mission and what time it was measured after that snowfall compacted. We can also take the standard deviation within a 10-kilometer box and make a really good map of what is affected by tides and what's not affected by tides. So we should be able to measure grounding lines really pretty nicely. I've done this at a course resolution now. We'll be able to do it much better soon. There's some great work that Helen and Matt and a group of other supporting players have done on the Amory ice shelf, looking at bathymetry of melt streams. So you can see the surface of the water here, which is a bright reflector, and then the volume of melt underneath it. That's a melt stream right there. This is more of a lake, seeing about 3 or 4 meters of water there. And then other kinds of lakes that you can see. Matt Siegfried has filled in the last of his lake time series with ISAT-2 measurements. Right, Matt? I'm not mischaracterizing this. So this is his lake with a history of ISAT measurements, GPS measurements, and then ISAT-2 measurements on the end. The data are available in a number of different forms. You can get geolocated photons, you can get land ice elevation, a variety of sea ice, land elevation, atmospheric backscatter, ocean surface ice, inland water from NSIDC. We'll soon have elevation time series products for ISAT-2 over land ice, and we'll be working towards gridded products. And a great way to get started is to look at the tutorials and tools that we put together for the ISAT-2 Hack Week last June, which a number of you were at. We're hoping to put together another one of those for this year, probably also in June, so watch CryoList for that. We've got 1,600 data users to date, close to 1 million files served just this year. So the summary of this is that we're doing great. The data are available, probably where you want them. The elevation change data are on their way soon. We're getting all kinds of new applications for this, and please, this mission is near and dear to my heart. Please go and do great science with it. So I'd like to thank my collaborators, and Thanks to you for getting me to be here.
Thanks so much, Ben. I think we'll wait for questions until the discussion and ask Aaron Stubblefield to come up to tell us about modeling active subglacial lakes.
Yeah, so today I'll be talking about modeling active subglacial lakes. And this is work that I've done with Tim Crates, Johnny Kingslake, and Mark Spiegelman as part of my PhD work at Columbia University. So the question that really keeps me awake at night is how do we study the evolution of subglacial drainage systems over time when they're covered by kilometers of ice? So luckily, in Antarctica, we have hundreds of subglacial lakes. Wow. And they turn out to do interesting things and potentially give us information about what the subglacial drainage system is doing. Here is perhaps my favorite example. It's from Siegfried and others, 2016. So thanks, Matt, for doing most of the motivating here. Yeah, so we're at the confluence of the Glen's and Mercer ice streams, and we have this whole system of subglacial lakes. And here on the right panel, we have elevation change time series relative to some regional background. And we can see that a lot of interesting dynamics are happening, but I wanted to focus on these top two right here, subglacial Lake Conway, this upstream lake, and subglacial Lake Mercer, this downstream lake. And so we can see pretty clearly that Conway is filling and draining over time. And if we look at Mercer, it seems like it's doing the same thing, but it has this interesting multi-peaked filling and draining event. And when I first looked at this, I thought, wow, they're filling and draining like roughly in sync. So either this is a very wild coincidence or they're somehow communicating with each other. And yeah, never believe in coincidences. So these results kind of inspired me to come up with a model of subaerial lakes that are connected by subglacial channels. Why did I start out with subaerial lakes? Because they're easier from a modeling perspective. Yeah, and so we have a couple subaerial lakes connected by subglacial channels. And what does the upstream lake do? So what I like to call the fundamental theorem of Yokolov dynamics is that if you have a glacial lake and you're just dumping water in, one of two things can happen. It can go to steady state, which is boring, or it can oscillate over time and have these filling and draining cycles. So this has been known and goes back to works from Nye and Fowler and was really inspired by Yokolov cycles in Iceland. But clearly something similar is happening in Antarctica. Okay, so it takes roughly 10 minutes to explain why this happens. So we're just going to take this as gospel, and I'll show you what happens for the second lake. So the downstream lake, it oscillates at the same overall frequency, but it has these, you can get these multi-peaked filling draining events under certain circumstances, if the downstream lake is of similar or smaller size. Okay, so the good thing about these models are that we have observations of lake depth, and from the models we can get a lot of information about what the channel is doing or the canal or cavity system or whatever. We can get information about the channel size, discharge, and pressure in the drainage system. And so, yeah, so this is meant to be similar to the subglacial Lake Conway and Mercer system from the previous slide. Let me back up real quick. So, but you'll notice here that the amplitude of these oscillations are much larger than what we see in the Antarctic system. And that's because the effective pressure boundary condition is going to look quite different for the Antarctic subglacial condition. So if I seem paranoid about pressure in a minute, it's because I'm very paranoid about it, and we need to get it right. So, yeah, what else did I want to say about this? I guess nothing. Okay, moving on. Yeah, so just to summarize the motivations, we have these surface observations of height change, and the first order of business is usually estimating the boundary of the lake and something about volume change rate. And I have a secret slide about this. You have to ask in the questions to see, because we don't have time. But looking forward, we want to be able to say something about subglacial processes in between the lakes, near the lakes, inferred from these surface observations. Okay, so now I'm gonna briefly go over the theory. The description for this section said something about new boundary conditions, so be careful what you wish for. So here's a picture of sketch of a model setup, and we assume that the stress at the ice-water boundary equals the water pressure acting in the inward direction. And if we can assume that the lake is hydrostatic, then we can decompose the pressure as the mean pressure along this interface, plus this extra term that has to do with deviations of the elevation of the interface. Okay, so important point number one, the mean water pressure is unknown. We don't know what it is. It's actually part of the solution to the problem. And we do not assume that this equals the ice overburden pressure, even though we expect that in most cases it will be quite close to the ice overburden pressure. But if the lake is actively draining or filling, then the water pressure could be under pressure or over pressured relative to the ice overburden pressure. Okay, so we have a boundary value problem with an unknown boundary value, which might make you nervous, but don't worry. Like I was talking about volume change rates, we have this additional constraint, and it states that the ice deformation normal to this interface must integrate to equal the volume change rate. Okay, and if you think about that for a few minutes, you can convince yourself why it's correct, but we don't have time to go through the derivations rigorously, but I can show you later if you're interested. Okay, so this is the basic theory and behind this problem, and let's keep going. So the basic strategy I'm going to be looking at is we're going to choose the volume change rate as just a constant to study basic behavior of the topographic evolution and the numerical accuracy. And actually, I shouldn't have put this. Well, we don't have time to do this, but it's another one of my secret slides you can ask about. Yeah, so I'm going to be showing you a lot of pictures that look like this. This is supposed to be a glacier, but there's extreme vertical exaggeration, and I only have 2 minutes left, but most of this is pretty straightforward and quite expected. So first I'm just going to throw up some results of inactive lakes, setting volume change rate equal to 0 for a couple different background flow speeds. And we get what we've seen before, a flat area over the lake. It's just like a mini ice shelf. And we get these interesting secondary features, trough and ridge pairs, that have been discussed in the literature. Okay, but we're here for active lakes, so let's move on. So here I choose a volume change rate of minus 90% of the initial volume in 1 month. And what happens? Well, what do you think happens? the ice surface depresses and forms this topographic depression, and yeah, it's an ice cauldron. So this is for a kind of slow flow regime. Fast flow regime, you get the same basic thing, except it's slightly more asymmetric due to the height change due to horizontal flow. Okay, so draining lakes, depressions, and so we want to know how close the upper surface and the lower surface correspond as the lake drains over time. This is a one-to-one line. If they're doing exactly the same thing, they're on this line. They're quite close. I can talk about this more later. Okay, filling lakes, what happens? So, same sort of thing, but you get this topographic bulge as the lake fills. Slow flow regime up top. Fast flow regime, same picture, a little more asymmetric. And so the same sort of free surface evolution diagram here. Deviation is a little bit more away from this one-to-one line. Okay, pressure deviations. Remember, I said I'm paranoid about the pressure. So this is deviations of the mean water pressure from the ice overburden pressure. So for the inactive lakes, we're basically at 0 for all intents and purposes. For the filling lake, we're quite close to 0, but we're slightly positive. For the draining lakes, we can deviate by several kilopascals. But who cares about kilopascals? Raise your hand. The effective pressure cares about kilopascals. So if we want to develop a reduced model for this, we kind of have to throw away this term here, and we have to correct for it somehow. So this is just something I'm trying to keep in mind. And all of these results are, I showed 6 examples, and we're just trying to generalize this more with scaling arguments and whatnot. So future work, the big one is coupling B dot to a subglacial hydrology model. That's going to be the exciting part. And thanks.
Thank you, Aaron. And we're going to stick with this quick speaker overturn. So next up we have Elisa Mantelli, who's going to keep us on the ice sheet base and talk about the case for subtemperate sliding.
So actually I've changed my title a little because I didn't want to make it so front and center, but we are going to get to the subtemperate sliding part at the end. Actually, the place where I want to start is slightly different than that, and it's really used this beautiful image. This is East Antarctica near the Totten Glacier. It's a radiogram from the UTIC group. You see the ice sheet all the way from the ice divide to the coast. And the thing that is striking here is that the layers, the internal layering that you see, not all the way to the bed, but far down the ice column. And so these layers are interesting because, from an ice dynamics perspective, because they form along with the ice flow, and so they carry information about the formation all the way down until you can see them. And so really, I'm going to ask a little bit of a provocative question here. That is, now, is it possible that since these layers record the formation, now can we use them to constrain ice flow at depth in a systematic way? Now, so this is a little bit of an ambitious question, like I said, and to be, and also a little bit vague to this point, but to make it more specific, now this is the point. We care about the formation at depth because what an ice sheet model cares about the most is traction near the base, and traction near the base is nothing but, it's related obviously to strain rates and the shape of your velocity profile. Now the way we do that typically in an ice sheet model is take information from the surface, velocity, so this is result, Tiger Strice paper by Olga Sergienko and Richard Heimer, typical example, take information from the surface and ice geometry information and invert for traction at the base. Now, we've said that there is information in the layers about this deformation at depth, and that's really what we're trying to get at when we do this inversion, deformation at depth. So can we use the layers to do a little bit better than what we do right now to get at this traction, whatever traction depends on. And again, this is, I'm not going to pretend that I have an answer to this question. I really want to cast it as a question to you all. And all I'm going to try and do today is to show that in a very, very simple case, we can try and use layers to get at information about traction at the base. And the simplest case that you can come up with is the case of a very sharp contrast in friction, in traction at the bed, that is the case of sliding onset. And so if you think of an ice sheet, and so this is my toy model for an ice sheet, so forgive me for being naive, but take an ice sheet flow line. Now you're going to have that in places the ice sheet is frozen to the bed and you have basal no slip, and then in other places as you move down and you make heat by internal dissipation, the ice sheet base is going to be at the melting point and you slide. And now if you think about it in terms of traction, and this C would be your friction coefficient, all you're saying is that there are places where the bed is very sticky, and so basically you have an infinite friction coefficient, a very large one. And there are places where you have an order 1 friction coefficient and some sliding law applies. So now the point is what happens when you splice these two regions together in this place here. Now the specifics of what happens there is not really important now, but the point to be made is that if you think about this in terms of velocity, what will happen is that you accelerate along the bed very rapidly. And this produces a signature in the layer that Hans Bergman recognizes what is known as the Bergman effect. And so you will have layers drawing down towards the bed very rapidly when this acceleration, so when you start sliding, and the opposite is true when you go from sliding to no slip. And so now all we're going to do is try and say, well, if we look at layers in the real world, and now can we use this signature in the layers to try and detect traction or friction changes and this abrupt onset of sliding? And the second question, this goes back to the point on subtemplate sliding, is while we do this, can we learn something about the physics of how these transitions work? And so to do this, we have essentially 3 steps that we need to take before we can actually try and do it for real. The first one is that we need a signature. So we need to know, in principle, in a model setting, what is it that we're looking for. And this we're going to do, I'm not going to go into any detail here, but the thing to keep in mind is that if you consider, if you use if we assume that an ice sheet is shallow, which it is in general, then you can go back here and say that you can zoom in this region near the onset and cook up a boundary layer model that describes rigorously the flow here around this transition region. And this is what we've done here. And the model that you're looking at is a Stokes problem near this transition point where you have a hard switch between basal no slip and a sliding law. 2 things that are important here. The first one, this would be a streamline of this model. And the first thing that is important is that if you go at this very short spatial scales, and so here we're resolving the thickness in the horizontal, your age equation, so what tells you the evolution of age in the ice sheet, reduces to an advection problem for age, and this simple advection problem tells you that streamlines and isochrons are exactly the same thing. So anything, if you look at very short scales, the 2 things coincide. Or if you look at it from a broader perspective, what you're saying is that changes in geometry of isochrons over short scales correspond to changes in streamlines. And so this is interesting because anything that we can say about the velocity field actually is something that we can say about the layers and vice versa. So this is point 1. And point 2, again, doing analytical work that I'm happy to discuss about if you wish later, we can look at really the flow very close to this transition point, and we can do asymptotics there, and we can figure out what is the slope of these streamlines. What we find is that streamlines are very, very steep, so they diverge, they become infinitely steep actually here near the transition point, and they depend on distance from the origin to this negative power. And so what this is saying is that we expect a very strong signature, so we're quantifying the Bergman effect here, and we expect a very strong signature in the layers that is very distinct and we can quantify. Now we can do a little better than this, so we can do numerics and actually solve this slopes problem. This is almost inessential if you wish, but this is our domain called no slip to the left of this dashed line, sliding to the right. These white things that you probably don't see are streamlines, and you see that, and the background is the velocity field. So here you have no slip, dark blue, and sliding. So 0 is dark blue, and then you have some amount of horizontal velocity here in yellow. You see your transition, you see your streamlines going down towards the bed like we expect. You can do a little better now and say, well, I want really to look for this into an ice sheet, so what I'm going to do. But I can plot the slope of these streamlines, and this is what this plot down here is. And you see this plume of yellow. These are very steep slopes, up to 20 degrees. And you can do even better if you slice this plot and you compute profiles of slopes as a function, so profiles of slope at different distances from the origin. You see this very distinct profile where you have very steep slopes at some point midway in the ice column. And the other interesting thing is that these slopes persist at some distance, like half of an ice thickness downstream of the origin. You're still going to see deviations from the background of 4 or 5 degrees. So it's big deviations from the background state. So now, if this exists, we should see it, right? Now, next question is, well, how are we going to see it? Okay, I'm really short with time. Sorry. How are we going to see it? Well, we're going to see transit with radar. Long story short, seeing something like this with radar is not easy because slopes that we care about are steep, and because we want to resolve small changes in layer slope, and we want the slope. That's the other interesting thing. So what we've done, something like that does not exist, so we've worked with colleagues at Stanford and figured out a smart way of process radar data, unique airborne coherent data. We have cooked up a new SAR processing technique that corrects, that actually gives what we want, and this is coming out on JBlock. Take home message, we can compute slopes, this is a map of slopes, directly from the processing, and we can do that with the accuracy that we require. Then the third ingredient is, well, we need to know where to go and look, because it's not obvious to say where sliding onset is. And so what we do is, well, we look at this institute ice stream region, primarily because the onset region there is on bedrock, and that makes our life much easier. And we run an ice sheet model, we invert for friction at the bed, figure out where ice flow is dominated by deformation and where instead sliding dominates, and we overlay this with beautiful bus grid 2010-2011 bus survey, and pick lines. So here you probably can't see the color, but we pick places that corresponds to transition from flow by deformation to flow mostly by sliding, and also we pick lines that are as close as possible to flow lines, because really the relation between layers and streamlines works well when you don't have lateral flow. Now, results, what do we see? So this is one of those lines. Black is ice surface, the bed from the radar. Open dots is surface velocity that's used for the inversion. Full dots is the sliding velocity. Now, as we expect, sliding velocity increases. The scale is here on the right. And then if we look at the slopes, now you can't probably see it, but here we have a place with red, which means that layers are sloping downward and the bed is pretty much flat. And here we have a place where layers are sloping upwards. Now, this is not exactly what we expect, because the velocity is accelerating, but we need to take bed topography into account. And so your streamlines will wrap around topography. And so what we do is say, okay, we're going to separate places depending on bed topography when we have topography over large enough scales, and deal with these two patches separately. And so if we then compute probability density functions basically of slopes for these two patches separately, and now look just at the shaded thing, you probably can't read the scale. But what this is saying is that if you subtract the bed slope to the slope of the layers, what we're going to get is that your layers are sloping downward in both patches relative to the bed. So basically this is what you're seeing. And they do so more the more rapid, the larger is the speed up that you have across your patch. What is the problem though? So the black thing down here behind is the distribution of slopes that you would get from a hard switch. And so the problem is that, sure, we do see that layers track velocity changes, but they do not do it the same way as we would expect them to do. So the way this hard switch should work. And here we get to the point of, this is the point that I was trying to make, but we also get to the point of subtemperate sliding that is really, the reason why this does not work is not because there is no information, but maybe because we need to revisit the assumptions that we started from. And so what we've done is say, well, take Bergman's take basically, and all ice sheet models take of an abrupt onset. But recent work that I've done is coming out, work with Christian Schulte is coming out next week, shows that this hard switch leads to no solution. And because the acceleration is so rapid that we freeze the bed again. And so really what we should do instead is to remember that friction coefficient depends also on temperature. This is something that is easy to forget because it seems to be such a little thing, these pre-melted films that exist only very close to the melting point. But actually what happens is that if you allow your ice sheet to know that, you end up with a transition region, and you see here your toy ice sheet, a transition region where sliding increases very slowly in space. And so this very slow onset is consistent, at least qualitatively, with less steep slopes. Now the problem though is that how less steep is hard to say. It's very hard to say because the moment we go at the ice sheet scale, layer slope are not only the result of friction at the bed, but also of topography and accumulation. And so really what we would need is an ice sheet model that uses boundary conditions like this to try and figure out if that signal is compatible with a distributed onset. Now coming to my conclusions very quickly, the one thing that I wanted to say here is that, and address this as a question to you, this theoretical work that we've been doing points very strongly to subtemperate sliding as a very important component of ice dynamics, particularly when it comes to the onset of streaming flow, and there is an instability that develops there that seems to be responsible for structure emerging in the flow and potentially tributary type flow, even in the absence of topographic constraints. So this is what the theory says. We don't know that this exists in practice. So, and what we've tried to do here is a first test of this. But this is not really a test. We just can say that sliding is not abrupt. But anything that you guys can do from observations would be absolutely great. And the second point is almost an essential one, that is that there is indeed information in the layers that one can use to try and get at friction at the base in a better way. That's all. Sorry for taking longer.
Thank you, Elisa, and we're just going to move right along to our final speaker, who is Felicity McCormack, and she's going to talk about the internal deformation of WAIS Glacier.
Thank you. That was a great introduction to my work, so thank you very much for that. So this is in collaboration with Roland Warner, Adam Trudeau from UTAS, and Ellen Zerusi at JPL, but it really builds on decades worth of work in the ice mechanics lab, observations of boreholes and ice cores, and modelling as well. So thank you to everyone who's come before me. So ice flows by a combination of basal sliding in the presence of meltwater, as we've heard a lot about over the last few days, but also deformation. I'm here to argue that deformation isn't negligible. And what do I mean by deformation? It's really the movement within and between ice crystals in response to an applied stress. We see that basal sliding is dominant over, as I said, over much of the grounded ice sheet. But deformation drives flow in the interior, where it's frozen to the bed, as Lisa has already talked about, and also dominates on ice shelves. So if you think about the extension of the ice shelf as it flows towards the ice ocean front. So deformation and sliding are both fundamental components of ice sheet models. And I'm going to talk a little bit about some flow relations for deformation. So what are flow relations? What should they incorporate? Basically, a flow relation measures the strain rate, so the response of the ice to an applied stress. And we usually look to laboratory experiments for this. So this is a figure here that shows when you've got a block of ice and you apply a stress, whether it's a shear stress or a compression or extension stress, what you see is that the ice responds by decreasing strain rate during this primary stage of creep until it reaches a secondary stage of creep at where the strain rate reaches its minimum. After that, the strain rates increase until they reach tertiary steady state creep. Now, there are three things that I want to point out about this. The first one is that in steady state flow, the strain rates are enhanced relative to secondary minimum creep. The second thing is that that enhancement is a function of the type of stress that you apply. If you're applying only compression, so stretching, squishing, very technical terms there, it's going to be, your strain rates are going to be less than if you apply only simple shear. The third thing that I wanted to point out, which you can't actually see from this figure, is that in the transition to steady state flow, ice is a polycrystalline material, so it has a preferred orientation of the crystal. We talk about that in terms of an anisotropic fabric. And we assume that the fabric, that anisotropic fabric, is compatible with the underlying stress regime. Now, perhaps the gold standard of flow relation would be to evolve individual ice crystals, but that's not computationally feasible at the continental scale or even basin scale. So we have this Glen flow relation, which is actually derived from experiments conducted only to secondary minimum creep. So it doesn't take into account the fact that the predominant mode of creep is this tertiary stage, where the strain rates are enhanced relative to secondary creep, and it has no information about the different impacts of different stresses on strain rates. Ice sheet modelers often combat this by introducing an enhancement factor, and that is somewhat arbitrary. It's often a tuning parameter, and it can range between greater than 1 to 10. You can set it at different values depending on where you are in your ice sheet, but not necessarily with a physical basis. There is an alternative though, which we've called E-star, which is empirical scalar tertiary anisotropic ice regime, and it takes into account this tertiary creep and the fact that the type of stress applied will lead to different strain rates. And I do that here, so the enhancement factor is E lambda S. Lambda S is a shear fraction, so basically what E-star does is it looks at any point in your ice sheet and it measures how much shear you have on a block of ice, and then takes into account also these EC and ES, which are compression and shear enhancement factors corresponding to this blue and this red line here, which we can get from laboratory experiments, and the ratio between them is very well known. So how much does it actually matter? To test this, I'm looking at weights, and I'm using the ice sheet system model, so we've implemented E-star and ISSM. It's also in ELMA if you're running ELMA and you wanted to use it. I don't know about the documentation, but you could read my paper. Also, ISSM documentation is pretty good. And the model domain is from Ellen's Cerisi's paper in 2017. What I'm doing is just inverting for basal friction using each of those two flow relations. Independently, it's very temperature dependent. And I'm just comparing diagnostic simulations of the two to look at the internal deformation regimes. And what I find, so I'm going to go through two key results. I'm going to keep it really short. And that is, so I've matched the simulated velocities to the observed in both cases. And what I really want to highlight is that both flow relations can capture the observed surface speeds, but they do it for very different reasons. And that, so these plots here show the fraction of flow that can be explained by deformation. 1 being 100% deformation, 0 being 100% sliding. And for the E-star flow relation, we see that deformation dominates in the interior of the continent, or interior of the catchment, where we see from Dusty's radar work that the ice is probably frozen to the bed and that there's not meltwater. And E-star predicts that deformation is driving, 80+% of the flow in this region. Whereas if we look at the simple Glen case, we see in the red contour there highlights the 0.2 fraction. So we see that Glen is actually sliding even in the interior of the basin, and that's because it can't generate this vertical shear because it's assuming that secondary minimum creep stage. The second thing we see is that there's a really sharp transition zone between deformation and sliding. But both flow relations show sliding here, and this is a region that we do think there is meltwater. And then the third thing, which is a kind of interesting result, and we have seen in some previous modelling studies, is that towards the grounding zone, we actually see more deformation in plates. And E-star shows that, you can get upwards of 30% of the flow contribution from deformation even in this region. Why is that? It's really about the contributions from basal shear and membrane stresses. So the deformation speeds here on the left and the corresponding basal shear stresses on the right. What we see is that the deformation is obviously very much strongly linked to the basal shear stress. Now, a few people have done some work on this. What I find is that the location of the highs in basal shear stress is probably what Olga has proposed, which is that it's about mechanical and subglacial hydrological coupling. But the magnitude of the basal shear stress, I propose, is a function of the magnitude of the enhancement or the rheology, with E-star showing higher basal shear stresses than Glen, and also less diffuse than Glen due to the role of the relatively more important role of the membrane stresses in Glen because it can't generate that high shear. A second key result is that in the absence of tuning for rigidity, the E-star flow relation can capture surface speeds better than the Glen over the ice shelf. And that's really because it can differentiate between spatial variations in stresses that are applied. So the black result here is E-star observations minus simulated surface speeds. Glen is blue, and Glen consistently underestimates the shelf speeds, particularly in the Thwaites Glacier tongue, where it's flowing quite fast and where we think it's going to matter, right, for ice mass flux over the grounding line. And as I said, that's really because of the impact of different stresses on the corresponding strain rate. So this is the shear fraction here, which is that fraction that I mentioned of how much shear is acting on any block of ice anywhere in your ice sheet. If it's equal to 1, then we're in a simple shear alone regime. If it's equal to 0, then we're in a compression alone regime. And what you find is that even in the shelf, there's some degree of shear in the shear margin, and then it'll lead up to the pinning point at the ice ocean front. We also saw previously that Glen predicts pretty much pure sliding over the grounding line, whereas there is some basal shear in E-star, such that the impact of shear stresses is kind of propagated in the initial stages of the ice shelf in E-star, whereas it's not so with Glen. And as a result, the E-star ice is softer, so it's more deformable than Glen across the entire ice shelf, but particularly in these fast-drying regions. Okay, now E-star is not necessarily the golden standard. There are zones where where the assumptions underlying E-star are not robust. You can read about that in my papers. But it does provide a physically motivated treatment of the impact of different stresses, shear and compressional strain rates. And I think this is the point. Like in ice sheet modelling, we really want to have good physical motivation for the processes that we're seeing. Tuning's great. I tune all the time. But what we really want to do is move towards being able to account for the physics. And I think E-star provides one step forward in this direction. And it also can capture the strain rate as evolution in response to different stresses if you're evolving your ice sheet over time. And I think that's one thing that we need to take account of when we do tune, is that a lot of these tuning parameters don't necessarily evolve with time. So they're not necessarily evolve as the ice sheet's responding to different changes in forcing. So where to from here? I definitely have an ulterior motive for modelling Thwaites, and that's if you can give me any radar or seismic observations relating ice crystal orientation fabric to vertical strain rates, that'd be wonderful. And if you wanted to collaborate on future field work to do this kind of thing, I'd be very keen to talk to you. There's obviously implications for ice shelf stability, the ice shelf being dominated by deformation. And, if we can nail deformation, perhaps we can go towards nailing basal sliding as well. We've seen hints of, what's the location and evolution of shear margins in these transition zones. And I really think that it's going to be addressing deformation and sliding in concert that can give us more insight into these processes. And that's it. Thank you.
Awesome. Thank you, Felicity. And I'd like to invite all of our session speakers up for hopefully a 10 or 15 minute discussion if we have time for that. And as a reminder, we've heard, in addition to the case for including deformation and the E-star model, we've also heard about ISAT-2, modeling active subglacial lakes, and then the relationship between end glacial layers and sliding onset. So anybody can find a way to ask questions that address all of those, I would be very impressed. So with that.
I have a question for Erin. So you showed in your modeling that you were able, to replicate what the satellite and GPS data show with the filling of Conway and the kind of 2 filling stages in Mercer. But there's also those predicted flow lines coming in more from East Antarctica, and I'm wondering if you think you would be able to incorporate that other potential flow pathway into that model, or if you've thought about that for your work.
I have not thought about that. What do you mean about flow pathways coming from?
Well, in the first map that you showed that we have all these linked hydrologic systems.
Yes.
We have Conway, and then that bright blue river. You could call it between Conway and Mercer.
Yes.
But then there's also from Mercer, there's another flow path coming down more on the trans-Antarctic side of things.
Yeah.
And I was just wondering if you had considered that potential additional input.
No, not yet. I mean, everything I've done, obviously, so far is very idealized. But the good thing about the framework that I've set up is that it easily generalizes to more realistic situations. It easily generalizes to arbitrary numbers of subglacial lakes. So yeah, that could definitely be something that I look at in the future. Yes.
So if you're going to do that, I strongly encourage you to take a look at some papers that were written over the last decade. Sasha was on some of them, talking about that exact thing, linkages between those lakes. There's a lot of work that's already been done, and it's great to hear that you're taking it forward, but just don't forget what's already been done in that area, because there's a lot.
Yeah, I've read most of the papers. That's what that inspired my dissertation so far. Yeah.
So I have a kind of broader comment, and I guess this was also relevant for yesterday too. And it's just how a couple of people did mention it. Chloe did, and I think Nick is also going to make this point, and Ben talked about the lakes. But it's just so amazing to see all of these results that have come from the merging of the satellite data and then the fieldwork on the ground. So with Torsten and Paul both in the room, and Alex, NSF, NASA, ESA, all coming together to help us understand the ice sheet. It's just kind of phenomenal. Wizard, Salsa, Thwaites program. I mean, none of this would have happened had we not had this long time series of satellite data. So really, yay. Yay NASA, yay ESA, yay NSF, everything coming together. It's really cool. Duncan, would you like to get to him? Tell me out your elbow.
This hopefully is a question that does link things together, but it's for Felicity. What are the impacts on frictional melt generation of applying E-star, and basically how that might link into subglacial hydrology?
Yeah, that's a really great question. I didn't even talk about it. Frictional melt. So I found it was really actually difficult to get my model to be stable unless I iterated between calculating the basal friction and the temperature. The friction coefficient was so incredibly sensitive to the temperature initialization, particularly at the base. Glen is it's pretty stable, but we see that it's not necessarily capturing things perfectly. E-star does predict higher frictional heating in the interior of the continent, where the basal shear stresses are higher. Generally, across the board, where the basal shear stresses are higher, but it can compensate for that a bit because of the impact of compression versus shear. And another thing that I found was that the deformational heating, particularly in those localized highs towards the grounding zone, was a lot higher in E-star than in the Glen flow relation, which means that sometimes you can get warmer temperatures in your ice column, like maybe even halfway down, which that's an interesting thing. But of course, this is a diagnostic picture; it's not the transient picture, and I think that there will be some adjustment. So it'll be interesting to see how that works out. Probably, perhaps more interesting in the ice stream than an unconfined basin like this.
Sort of, to follow on to Helen a little bit, we know how ISAT2 will play into Aaron's work. How can ISAT2 play into improving these models? Elisa's using radar. Is there a way to does the fidelity of ISAT2 make this easier for you?
So I can try and tell you, I don't know how to phrase an answer in terms of ISAT2. I can try and tell you what I can predict that should happen. And one thing that I think is very interesting that this September region should do is a concave surface profile. And it's very shallow, but so it's not concave down, it's concave, it's looking upwards. And so this is something that perhaps you guys may try to get at. Of course, the problem, like the thing that I said at the end very, very briefly, is that I can tell you what I expect in an idealized setting where I make an ice sheet with a flattish bed. There is the old point of topography, and so to make a prediction that we can test for real against observation, we would need to be able to do this in an ice sheet model, because I am the first one to say that this is all idealized work. And so we know that that signature exists. How strong it is in reality, I don't know. That is one thing. The other thing that we predict is that there should be a signature in water patterns, and that radar can help too, I think, and that's something we've been talking about with Winnie, for instance. So like the subtemperate regions are places where you do have some meltwater, but not a lot of meltwater, and it should be very distinct from a place where you have fully temperate sliding, because the point is that your basal energy budget kind of wants to stay at the melting imbalance there. So you don't have a lot of energy for making water or drainage. So maybe there is also something related to all the drainage aspect that one could try and get at. And then there is thermal aspects, but that is really hard, like Felicity also said. For models, that is at the edge of impossible. So you can produce anything and everything about basal temperature with an ice sheet model, depending on what you do on geothermal heat flux. That's pretty much it. But I think that the surface part would be interesting and very distinct. That's the answer.
Felicity?
I mean, I completely agree with you. It's really topography and temperature. But I think there should be ways of being very clever with surface elevation to back out basal topography. I don't know. I mean, I think we've got so much data, and we've got computational power, and we've got great brains, and we need to work together. I think that's the thing. Yeah.
One thing that I'm going to say, the other thing that one could imagine is not from ISAT, but actually to do actual field work through the borehole and measure strains. And that's the problem is that you need to know where to do that. And that, to me, is the bigger question right now. And so the reason of trying to look into layers and larger scale patterns. But
I was going to ask Felicity what the E-star model does to the shape factor, so the relationship between surface velocity and depth average velocity in these areas that have gone from sliding to not sliding between the Glen model and the E-star model.
So So I haven't actually looked at the depth averaged velocity, but I guess, wow, I'm not quite sure how to answer that.
So
Yeah.
it would lead you to something that you could measure at the surface in terms of the relationship between flux divergence at the surface and surface elevation change. If you could see change in velocity over time, so that would be sort of a diagnostic thing that would let you understand what was going on in your model, as long as there is a difference. I mean, if the E-star changes are all concentrated at the bed, then sliding and deformation then start looking a lot more like each other.
So I had a question for maybe like Ben and Felicity. I think we can chime in too, because I've heard a lot on how ISAT2 can help with its DHTT, can help mass conservation techniques, and I was wondering what like the mission could provide to like make that easier for ice sheet modelers. If you had any thoughts on that, because you mentioned that ISAT2 would be really helpful to get better fit topography, for instance, because it just provides better DHTT. Or is the existing data just good enough?
I'd imagine that not everybody has seen the existing data.
Oh yeah.
We have plans to come out with a gridded elevation change product, which ideally would be something that could be directly matched or not matched with the model. But that's maybe a few months in the future.
I think if anybody has any more questions, maybe we can ask our speakers in our next short break, hopefully. But let's thank our speakers once again, and we're going to have 5